Hello, today we start discussing 6.3 theorem. If f belongs to R alpha and g belongs to R alpha on AB, then fg, the product of two integrable functions, that is again integrable on AB. And we have modulus of f. Modulus of f is defined as modulus f of x equal to modulus of f of x. Okay, that is also integrable. And modulus of integral is less than or equal to integral of the modulus. These are the three things we need to show, and we start with the proof. We already proved in the last class if phi is continuous, f is integrable, then phi composition f is integrable. So we use that theorem, theorem 6.11. I think theorem 6.11. That is the composition of the continuous and integrable function. So we start with in that theorem we've set phi of t is equal to t square, and we'll if you take phi and if you take f belongs to R alpha, implies theorem 6.11 implies, since this phi is continuous and f is integrable, then phi composition f belongs to R alpha. Consequently, what is phi of f? That is f square. F square belongs to R alpha. That means if f belongs to R alpha, we have f square belongs to R alpha. Okay. Now we write the product for fg. What is 4fg? 4fg can be written as f plus g whole square minus f minus g whole square. Okay, so this is 4fg. We know that f and g are integrable, then f plus g is integrable. So this quantity is integrable, and using this fact, f is integrable, then f square is integrable, then the square of this f plus g is integrable. Similarly, we have already shown that if g is integrable, then minus g is integrable. Therefore, f minus g is integrable, hence its square is integrable. So this is the difference of two integrable functions, then that is also integrable. So this implies 4g is integrable. 4g is integrable implies fg is integrable, because 1 by 4 times 4g is integrable, then this will belongs to R alpha. So this proves A part. Okay. Now we will prove the B part. To prove B part, we first show that this mod f is integrable. For that, we take phi as phi of t as mod t. Okay, so we know that mod t is always continuous everywhere in the real line. So if we take continuous function as phi and we take f belongs to R alpha, then this implies that mod f belongs to R alpha. So that is the immediate consequence of theorem 6.11. Now we will show that the integrable, the inequality involving the integral of f and mod f. Okay, so for that we choose c such that c is plus or minus 1. Choose the c such that c times integral f d alpha is greater than or equal to 0. That means if you are given f and if integral f is positive, then c is taken as 1. Otherwise, choose t as minus 1. If this integral is negative, then choose c as minus. So this will be always greater than or equal to 0. So this is the selection of c. Now we have modulus of integral f d alpha. Okay, so this is equal to c times integral f d alpha, but we know that this the modulus of this is always plus or minus f integral f d alpha. We have chosen c such that this quantity is positive. So c integral f d alpha is always positive. Okay, so this is because c times integral f d alpha is same as plus or minus, or otherwise you can write it as modulus integral f d alpha. Okay, that's selection of the c. So we have this result, which is equal to c integral c f d alpha, and which is less than or equal to integral mod f d alpha. That is because cf is plus or minus f, because c is plus or minus 1, then this will be plus or minus f, but plus or minus f is always less than or equal to mod f. Okay, so this quantity is always less than or equal to mod f, then integral follows the same rule. So we have modulus of integral f d alpha is less than or equal to mod f d alpha. Okay, so this proves modulus of the integral is less than or equal to integral of the corresponding modulus. This proves theorem 6.13. Now we have a definition 6.14. The unit step function, that is denoted by I and is defined by I of x equal to 0 when x less than or equal to 0 and 1 if x greater than 0. So that is if this is our x-axis and y-axis, so the I of x can be the graph of I of x will be like this. If x is less than or equal to 0, that will be this part. This is the images of I, and this will be the image of I when x greater than 0. So this is the step function. This can be considered as a step function. You since this length is 1, we call it as a unit step function. So this is the definition of I of x. Okay, using this definition we will prove the next theorem, theorem 6.15. This is the statement of theorem 6.15. If a less than s less than b, f is bounded on ab, f is continuous at s, okay, and alpha of x defined in this manner, alpha of x equal to this I of x minus s. So alpha of x is, if we consider the interval AB, suppose this is our AB, and we choose a point S in between them, then this alpha of x defined as, at the point S we have up to this point the value is 0, and up to this S the value is 0, and at this point onwards the value is 1. Okay, so this is the definition of alpha of x. So this is our 1, and this is the graph of alpha of x. Okay, if this is the case, then integral over AB f d alpha with respect to this is a monotonic function, monotonically increasing function. So this integral will be f of s. So the only required conditions are f should be bounded and f is continuous at s. Okay, so we consider alpha of x, and we can prove that this integral is f of s. Okay, so we prove this by starting with a partition. So for the proof we consider the partition P. P consists of x0, x1, x2, x3, where this x0 equal to a and x1 equal to s, which is less than x2, less than x3, which is equal to b. You just consider this partition. Okay, then you can easily get what is up f alpha. Okay, so what is up f alpha? Up f alpha is the upper sum. So this is, in fact, this is sigma I equal to, or the other way you can write it as m1 times this x1 minus a, or s minus a. So this is our s minus a. Instead of writing x1, we write s minus a, plus m2 times this this is x2 minus s, plus this m3 times b minus, that is x3, that is b minus x2. Okay, so this is the upper sum. Now just consider these things. Okay, what is this m1, m2, m3? Sorry, here we have alpha of s minus alpha of a, alpha of x2 minus alpha of s, alpha of b minus alpha of x2. So this is the upper sum. now we just evaluate what is alpha of s minus alpha of a. Okay, alpha of s is 0, alpha of a is 0, so this quantity is 0, so we will have 0 here, plus m2 times what is alpha of x2. Alpha of x2 is equal to, x2 is here, which is greater than this s, so alpha of x2 equal to 1, and what is alpha of s? Alpha of s equal to 0. Okay, alpha of x2 equal to 1, alpha of s equal to 0, so this quantity will be m2 times 1, and this quantity is also 0, because alpha of b and alpha of x2 have the same values 1, so this difference is 0, so this value is always m2. Okay, so if you consider partitions like this, you can get the upper sum as m2. Similarly, you evaluate lower sum corresponding to these partitions, you can get the same manner. The only difference is these are the small mi as m1, m2, etc. So you can get the small m2. Okay, so these are the values of upper sum and lower sum. Okay, but we know that this what is this m2 and capital M2 and small m2. Capital M2 is the supremum value of supremum over x belongs to this interval x2. We have this what is the interval, and corresponding to this x2 comma s. So this is our interval f of x. This is the capital M2, and what is small m2? Small m2 is the corresponding, so infimum x belongs to x2 comma s f of x. Okay, now you consider we are given that this f is continuous at s. Okay, so if you consider all partitions and this m1 m2, if you consider the refinement of these partitions, okay, by inserting points in between these, we are setting that this x1 equal to s and x0 equal to a and x2 is just greater than this s, and b is equal to x3, and insert points to get the refinement of these partitions. Then whenever you consider any partition of any refinement of this partition, you can get UPF alpha and LPF alpha as capital M2 and small m2 respectively. Okay, but if whenever this x2 converges to this s, okay, since f is continuous at s, we see that this m2, capital M2 and small m2 converges to f of s. Okay, as x2 tends to this s. Okay, whenever this point, this quantity, this x2 tends to, or the next point in the partition after this s converges to s, we can get this capital M2 and small m2 converges to this f of s. Okay, so that is because of the continuity of this f at s. This is because if we consider the interval sx2 here, and suppose this is our function, the behavior of function f in this interval, then you can get this is the maximum value capital M, and this is the minimum capital M2, and this is our small m2. Okay, so that is the maximum value of f and minimum value of f. Whenever this x2 tends to this point s, you can get the maximum tends to this f of s, this is our f of s, and minimum also tends to f of s, because if you shrink this interval by inserting points here, you can get the maximum value and the minimum value converges to this f of s as well. Okay, so we can say that since this f is continuous, at s, this m2 and small m2 converge to f of s. Okay, as x2 tends to s. As this interval shrinks, you can get this m2 and capital M2 and small m2 coincides with this f of s. Okay, and now we have this in fact this the limit of, or limiting case of this UPF alpha and LPF alpha is nothing but the integral. So this have integral to be f d alpha will be f of s. Okay, so this is the limit of this UPF alpha or infimum of UPF alpha, and supremum of LPF alpha will be f of s. Okay, so this proves that the theorem 6.1 integral a to b f. What is the meaning of this? This is nothing but the approximation of this integral. If you select this integral, if you consider the integral with respect to some unit or a step function, you can get the value of integral as the functional value itself. Okay, so if you use this alpha of x as the monotonically increasing function, which is a step function or unit step function, then the integral will be coincided with the functional value. Okay, so that is the meaning of this theorem. Okay, using this theorem we will prove the general case of this. Okay, in the next theorem 6.16 we will prove the general case of this. This is theorem 6.16. This is the generalization of the theorem 6.15. Suppose Cn's are positive real numbers, Cn greater than or equal to 0 for all n, and sigma Cn is convergent. So this is an infinite series, sigma n equal to 1 to infinity, Cn is converges, and these are the points. Sn is a sequence. Sn is a sequence of distinct points in open interval AB, and we define alpha as the summation n equal to 1 to infinity Cn I of x minus Sn, and if this f is continuous on AB, then we have, or we can approximate this integral as the limit of finite sums, or this series. Okay, so these are the functional values, the series of the functional values. So we find the value of this integral with this infinite series. Okay, so first of all, one thing we need to understand that what is this alpha of x. Okay, alpha of x is in fact a monotonically increasing function, because we identify this alpha of x. Alpha of x is a infinite series, say c1 I of x minus s1 plus c2 I of x minus s2 plus and so on. Okay, so if we have AB here, and suppose we choose s1 here, s2 here, s3 here, these are the points of this AB. Now you define I of x minus s1, or c1 times I of x minus s1. What is the graph of this? This will be like this up to this point. I will write it here itself. So what is c1 plus c1 times this I of x minus s1. Okay, I of x minus s1 is like this. At the point s1 we have the value 0. After this we have 1, and if we consider this function, after this point s1 we have c1 times 1. So that will be like this. This will be the graph of I of c1 times I of x minus s1. Okay, so this is the graph. I will put it here. Now you consider the second thing, c2 I of x minus s2. So for this function up to this point s2 we have 0 function, 0 value, and after this s2 we have c2 times this. Okay, if c2 is some value less than, suppose this is our c1, and suppose we have up to this point we have the value c2. Okay, now you consider the sum of these two. How do you get the sum of these two functions? Okay, so if you add these two functions, you can get the graph of that function as if this is a and this is b, this is s1 and this is s3, this is s2. When you add this up to this point, we have up to s, the value 0. From s1 to s2 we have c1, s1 to s2 we have c1, and s2 to b c1 plus c2. So that is somewhere here. Okay, so that is this is the sum of first two terms of this alpha of x. Okay, so if you consider the first 3 terms, okay, you consider next one, c3 times I of x minus s3, then what is I of x minus s3? Up to this point, up to this s3 we have 0, and from s3 onwards the value is c3 times 1. So that will be somewhere here. If C3, if this is C3, then from S3 onwards, our function of our value, function of the value of this C3 times I of x minus S3 is this. Okay, so now you consider some of these three. Okay, how do you draw that graph? So that will be like this. If you consider A here, and this is our B, this is S1, S3, S2. Okay, so now you need to add all these things. Okay, so from S1 we have 0 here, and S1 to this S3, that is C1. Okay, S1 to S3, that is value C1, and this S3 to this point, S3 to S2, we have this much value. S3 to S2 is the sum of these two quantities. Okay, you need to add this, so that is somewhere here. Okay, and S3 to B, we need to add these three things. Okay, so that will be like this. So when you consider these three terms of the alpha of x, then that will change us to this one from this. Okay, this will be changed to this. So when you consider the infinite terms, you can get our alpha of x as like this. Okay, so this is a step function. So this is monotonically increasing function. So first you identify that this alpha of x is a monotonically increasing function. Okay, and one thing, another thing is, if you consider the series for this alpha of x, then alpha of x is a infinite series. Then using the Weierstrass test, you can get this modulus Cn of I of x minus Sn. This is always less than or equal to Cn. Okay, mod Cn, which is equal to Cn, but we know that sigma Cn is convergent. Therefore this alpha of x is also uniformly convergent, or the series is uniformly convergent. So this alpha of x exists. Okay, so this is a convergent series, hence this alpha of x is defined, and which is monotonically increasing. Okay, and another observation is alpha of a. What is alpha of a here? When you consider alpha of a, it contains I of a minus Sn. Sn is always greater than a, therefore a minus Sn is always less than 0. Therefore I of a minus Sn is always 0. So every time will be 0. So this will be 0. When you consider alpha of b here, then b minus Sn is always greater than 0. Okay, so because Sn is always less than b, so this quantity will be always 1. Therefore this is nothing but summation I n equal to 1 to infinity Cn. So that will be our alpha of b. Okay, so these are the immediate observations of this hypothesis. Now we need to prove that this integral is same as this sum. Okay, so how do you get this one? Okay, we will prove that the limit of the sum of this infinite series will be integral a to b f d alpha. That is to prove integral a to b f d alpha and sequence of partial sum of this. Okay, that is summation n equal to 1 to some capital N, this Cn f of Sn can be made less than epsilon. Okay, so for every epsilon greater than 0, there exists n such that this quantity, this sequence of partial sum will be less than epsilon. Okay, or some constant times epsilon. Then this will prove the required result. So in order to prove that, we start with epsilon greater than 0. This is our epsilon greater than 0, and choose n such that, and so that summation n plus 1 to infinity Cn is less than epsilon. Okay, this is possible because we are given that Cn is convergent. Sigma n equal to 1 to infinity Cn is convergent. Okay, what is the meaning of that? The sequence of partial sum, I will put it as Tn, so that is this will be Tk. What is Tk? Summation n equal to 1 to k Cn. Okay, so this is our sequence of partial sum of this. We have seen that this Tk converges to summation Tk converges to sigma n equal to 1 to infinity Cn. Okay, so this converges to this sequence of person converges to this one. Okay, what is the meaning of this? A sequence converges to this number means for every epsilon greater than 0 there exists n such that this Tn minus summation or the other way, summation n equal to 1 to infinity Cn minus T k modulus of this less than epsilon for all k greater than or equal to n. Okay, so this is the definition of the convergence of a series. So this is true for k is equal to capital N as well. So that is sigma summation n equal to 1 to infinity Cn Cn minus Tn. Okay, T capital N is less than epsilon. Okay, this is nothing but sigma n equal to small n equal to capital N plus 1 to infinity. Cn is less than epsilon. That is because this Tn is nothing but summation k equal to 1 to capital N Ck. Okay, so this is our Tn. So this small n is equal to 1 to capital N Cn. So, this is our Tn. So you just subtract from this, then you can cancel the first n terms of the series. So that remaining terms or the tail end of the series is always less than epsilon. That is the consequence of this one. Okay, so we can easily get n such that summation n plus 1 to infinity Cn will be less than epsilon. Okay, now we put alpha 1 of x equal to summation. If you are once you are identify this n, you define alpha 1 is summation n equal to 1 to capital N. Okay, Cn alpha of x minus Sn, and you define alpha 2 of x. What is alpha 2 of x? The remaining part, n equal to n plus 1 to infinity Cn alpha of x minus Sn. Okay, now we have if you consider the integral a to b f d alpha 1, okay, integral of f with respect to this alpha 1. Okay, obviously one thing is obvious, this alpha 1 plus alpha 2. What is alpha 1 plus alpha 2? That is nothing but alpha. Okay, it's summation n equal to 1 to infinity Cn I of x minus Sn. So we split this alpha using this capital. That is what we have defined here. So you consider integral a to b f d alpha 1. Okay, what is that? That is sigma integral a to b f d of what is alpha 1? That is C1 I of x minus S1 plus etc etc. Okay, so this can be written as integral a to b f d C1 I of x minus S1 plus integral a to b f d C2 I of x minus S2 etc. integral a to b all the way up to n. Okay, f d c n c capital N minus c capital N I of x minus S capital N. Okay, so this can be written as the C1 can be taken out, then the remaining will be f of S1. That is our previous theorem. So this can be written as C1 times f of S1 plus the C2 can be taken out, C2 times f of S2 plus etc. Cn times f of Sn. So this can be written as summation I equal to 1 to n capital N this or n is equal or Cn is n is equal to 1 to n Cn f of Sn. Okay, so this is from the previous theorem 6.15. In that theorem we have shown that in case of this alpha contains one term. Okay, so the next will be what is when you consider the alpha of alpha 2, what is alpha 2 of b minus alpha 2 of a? Obviously alpha 2 of a is 0 because if you put a here, then this quantity will be 0, then all the term will be 0. So alpha 2 of a is equal to 0, and alpha 2 of b will be summation n equal to n plus 1 to infinity. Okay, when you put b here, then this quantity will be 1. So the alpha 2 of b will be this. Okay, n equal to n plus 1 to infinity this. But we have chosen this n as this quantity is less than epsilon. So this will be less than epsilon. Okay, this is the splitting of alpha 1 and alpha 2, and this implies since this quantity is less than epsilon, you can get modulus of integral a to b f d alpha 2. Okay, we have shown that, or we have seen the estimate of this. This can be written as m times alpha 2 of b minus alpha 2 of a. This is the estimation for this, or this is an upper bound, and we have seen that this quantity is less than epsilon, therefore this will be m times epsilon. Okay, now now we can prove the convergence. You consider integral a to b f d alpha minus summation n equal to 1 to capital N c n f of Sn. Okay, so this can be written as integral a to b f d alpha 1 plus integral a to b f d alpha 2 minus summation n equal to 1 to capital N c n f of Sn. Okay, but we know that this integral a to b f d alpha f1, f d alpha f1, what is that? That is this one. So that can be written as summation n equal to 1 to n c n f of Sn. Okay, so we can cancel these two things. We have seen that these two quantities are the same. So the remaining will be integral a to b f d alpha 2. But this quantity is less than m epsilon. So this is less than m epsilon. So every epsilon greater than 0, there exists n such that this is the sequence of partial sum of our series. So this minus this quantity is less than m epsilon, which implies the sequence of partial sum converges to this. Okay, or integral a to b f d alpha is the sum n equal to 1 to infinity cn f of Sn by definition. Okay, so this is the proof of theorem 6.16. okay, in the next class we will discuss the 17th theorem. In the theorem we will show that some interconnection between Riemann integral and Riemann Stieltjes integral. Thank you.